Today, we're going to connect the dots between a really common software pattern and the deep underlying principles that actually make it work so well. We're going from the practical code we all write every day to the core ideas that explain why certain approaches just crush it in our modern, complex world. So let's dive right in. This quote from Bartosz Milewski, it just perfectly captures this quiet crisis that's been brewing in software development for a while now. The hardware has changed, the world has changed, but the question is, have our methods really kept up? And this is really the heart of the problem. For decades, our software just got faster because the processors got faster. But that era, it's over. Now, speed comes from doing a lot of things at once, using multiple cores. That's parallelism. And this whole multi-core revolution is putting our old ways of coding, which were really built for a single-track world, under some serious strain. And that leads us to what we can call the boiling frog problem. The water is definitely getting hotter for one particular way of doing things, imperative programming, which is all about side effects and constantly changing state. So, here's the thing. The very tools that used to help us are now kind of becoming liabilities. When you've got multiple cores all trying to change the same piece of data at the same time, well, you get chaos. Our old school solution was to use locks, basically telling other processes, hey, wait your turn. But locks just don't scale, and they often create brand new headaches like deadlocks. You end up causing more problems than you solve. Okay, so if that's the problem, what's a real solution? Well, let's look at a super powerful architectural pattern Martin Fowler talks about, event sourcing. And it offers a completely different way to think about the state of your application. Instead of just storing the current state of your data, the final answer, you store a complete, unchangeable history of every single thing that ever happened to it. Every action, every tiny update gets recorded as an event. And check this out because this slide just nails the difference. On the left, with the traditional way, you only know where the ship is right now. The entire history of its journey, gone, poof. But on the right, with event sourcing, you have this perfect auditable log. You know the whole story, not just the last page. And the benefits you get from this are just immense. First off, you get a perfect audit trail for free. Debugging becomes like a superpower. You can literally replay the exact sequence of events that led to a bug. Then you can fix your code and just rerun the log to fix the state. I mean, this is a total game changer for building systems you can actually rely on. So, event sourcing is an amazing, practical tool, no question, but it works so well for a reason. It's tapping into a much deeper, more fundamental idea about programming itself. So let's peel back one more layer, shall we? And that deeper idea is composition. According to Milewski, this isn't just some technique, it's the absolute essence of what we do as programmers. I mean, this is just how our brains are wired to work, right? We can't deal with giant, tangled messes of code. We need structure. So we break big problems down into small, manageable chunks, we solve them one by one, and then, and this is the critical part, we have to be able to put those pieces back together again, reliably, to solve the big problem. But here's the catch. For that recomposition to actually work, the output of one piece has to be a valid input for the next. The ends have to fit together perfectly, like puzzle pieces. If they don't, the whole thing just falls apart. And this is a brilliant illustration of why we need things like strong type systems. Without them, we're basically just monkeys randomly hitting keys and hoping something good comes out. A type system is that barrier, that quality control that checks if our puzzle pieces even have a chance of fitting together, catching errors before our code even runs. It makes sure our compositions are actually sound. So how does this big idea of composition connect back to our boiling frog problem? Well, it helps us see that there are really two fundamentally different worlds of programming, the imperative and the declarative. Imperative programming is all about giving the computer a step-by-step recipe. Do this, then do that, then change this. It's very local thinking. Declarative programming is totally different. You don't describe the steps, you describe the result you want, the final state. It's a much more global, big-picture way of thinking. So this is the imperative world. It's a lot like classical physics or a classic video game. We know the ship's position and velocity right now, and we calculate where it will be in the next tiny fraction of a second. It's all about a sequence of small local changes. And then there is the declarative world. Here, we're not calculating step by step. We define the start, the end, and some global rule, like take the path of least resistance, and the entire trajectory just emerges from that definition. It's a profoundly different perspective on the same problem. And right here, this is the connection. Event sourcing is a declarative pattern. It doesn't tell the computer how to mutate the state. It just declares that the state is, by definition, the sum total of all the events that have happened in the past. It's a global definition, not a local recipe. Okay, so let's tie all of this together and see why this difference is more important today than it has ever been. It's all about building software for the world we actually live in. So what's the big takeaway here? What's the main thing you should walk away with? It's really about how all these ideas snap together. Look, the multi-core world we're in now makes that old imperative style of changing state incredibly difficult. It just leads to chaos. So a pattern like event sourcing comes along, and it's a solution precisely because it's declarative. By building on an unchangeable log of events, it's inherently safer to compose and scale. This isn't just a new technique, it's a fundamental shift in how we need to think about building software. Ultimately, this is the whole thing right here. That shift from telling the computer how to do things step by step to simply describing what we want to achieve. That is the key. This declarative mindset is what's going to let us build systems that can actually keep up with modern hardware and modern complexity. And that leaves us with one final big question to chew on. As we face more and more complexity, is the future of programming about getting better at writing recipes? Or is it about getting better at describing our dreams?